Thank you very much. So, can you see my screen right now?
Yeah.
Okay, great. And thanks very much for the invitation, and thanks everyone for accommodating my time zone by having this late seminar. So today I'll be indeed discussing this model of symmetric three-speed ballistic annihilation. And the content of my talk is based on a few works that you can find on arXiv, both with J.Haslegrave, who is currently in Warwick, and with Vladas Sidoravicius. So as you may know, Vladas sadly passed away last year. We had just finished our main paper on this model. And actually, this whole project started with one of Vladas' favorite open problems that he enjoyed very much sharing around. So we'd like to start this talk by sharing this problem with you as well, even though you will see that that it underwent a series of modifications before we get to the actual model that we'll be dealing with, that is three-speed ballistic annihilation. So this open problem is the following. It's called the bullet problem. Well, it's been nicknamed like this. It actually started as a riddle set by a software engineer called David Wilson. It was published online on a forum in 2012. It goes as follows. Imagine that you have a gun shooting bullets. So there is one bullet per second that is shot, all in the same direction. It's a one-dimensional problem. Only thing is that bullets have random speeds. They are constant over time, but each bullet is given a random speed. Let's say it's uniform on 0, 1 and independent from the speeds of the other bullets. And their interaction consists in annihilated when two bullets collide. So say that the first bullet is shot, then the second bullet, if it's faster, it might catch up with the first one, and then they would annihilate, unless the second bullet is itself caught by a third bullet that would be even faster. So you have this kind of dynamics happening. Graphically, you can make a space-time diagram as follows. So at every second, say, so the bullet is shot, and it goes forward in space with a slope that corresponds to its speed. So the slopes are i.i.d. and uniform on 0, 1. And in order to resolve collisions, you just look for the first collision that happens. Then you eliminate those bullets, and you just look at the next collision and so on. So you get this kind of process. If you look at a larger configuration, so this below is 500 bullets. And in this configuration, you can see that there is a one bullet here. Actually, it should go further. That is still flying at the end of this simulations. You have also two bullets there that flew for quite a long time, for 200 and so seconds, but eventually met. But this one is apparently still flying. And the obvious question here is, will some bullet, for instance, will the first bullet survive forever? Is there a chance that all the bullets flying after this one, even if they are faster, annihilate together, so that the bullet keeps flying forever? And this is, for now, as far as I know, a fully open question. Is it clear so far? Okay. So the as you can see, the combinatorics is quite complicated here. In fact, it's important to notice that it's not just a matter of ordering of the speeds. It's not enough to know which speed is faster than which one in order to resolve the collisions. You really have to take care of the value of the speeds. And that makes it quite tricky. Actually, there is no simple formula that would be a kind of sum of well, there is no algebraically simple way to tell from a collection of velocities, what happens in the end? You really have to work by induction, and that makes things a little bit complicated. The geometry quickly gets complicated, and actually you might think that this problem is just open because it's too complicated, too cumbersome, and that there is nothing really doable about it, really tractable. But still, there are indications that some interesting structure lies behind, and that happens when you consider a finite number of bullets. So consider an even number of bullets, of course. 2n bullets. What is the probability that they all annihilate? So this was among the initial questions that were asked on some forums, and you can look at this question appears in Math Overflow, it appears on Reddit, it appears on some IBM forum where they have riddles. So what is the probability that they all annihilate? It turns out that there is a very simple answer. It's very combinatorial looking. You can interpret this answer as with simple random walk or anything. But what is quite mysterious still is that there is, on the other hand, no simple proof for this. There is no bijective matching, for instance, between the problem of bullets and some simple random walk or discrete tree or anything. And this result still was proved. It's proved, in fact, in this paper, I can show it here. It's been proved by Brutin and Marquer. And the proof is surprisingly, like they say in the abstract, the proof is surprisingly intricate and mixes combinatorial and geometric arguments. It's really a proof that works by small deformation of the process, that it boils down to something that you can compute by induction. But there is really no direct argument. In fact, this paper proves furthermore, it gives furthermore the whole distribution of the number of surviving bullets, which is also explicit. And so the existence of this simple solution, even though there is no simple proof, suggests that there is something interesting behind, that might be a hidden structure that has yet to be found. Also, it's interesting to notice that in this paper by Brutin and Marquer, what they prove also is that this answer is rather universal in several ways. In particular, it doesn't depend on the distribution of the speeds. Here, we chose them to be uniform. In fact, it doesn't matter. And still, I recall that the model truly depends on the model does not only depend on the ordering of the speeds. So it's not just because the distribution of the order is uniform. There is really something specific, some kind of recombination of events that is happening, and such that in the end it doesn't depend on the distribution of the speeds or even on the distribution of the spacings. Here I took unit distance between bullets. It could be any distribution, and you would get the same answer in the end. So that's at the moment is known, but it's still kind of mysterious. But at least it suggests that there might be a nice solution for the problem, and that there is some more to understand about it. And another reason why it should be interesting, another less formal reason, is that it's also been studied by physicists, although in a different setting. Actually, they consider a model where you switch time and space compared to here. So horizontal would be space, vertical would be time. In other words, at time 0, you have particles at every integer location. And then this particle starts flying at time 0, again with i.i.d. velocities that are kept constant over time. And they annihilate when they collide. The interest in this setting, which is known as ballistic annihilation, that now it makes perfect sense to symmetrize the problem by having particles also on the left hand, on the left axis, on the left part of the axis. So particles now start from the whole real line, and it also makes perfect sense to have negative velocities. So in particular, you get this transition invariance, which can be helpful, and you can get also symmetry by mirror. That can be also very helpful in the study. In particular, if you have velocities that have a symmetric distribution. So this is typically what it would look like. So in this case, I chose the xi's to be given by so the initial location to be given by a Poisson point process, but of course it can be any point process. It can be integer location as well. If you look at a finite configuration and you have this kind of behavior here, and what is of interest to physicists, or what was of interest to physicists since this model was started in the 1990s, was in particular the speed of decay of density of particles. In this case, if you take mu to be a continuous distribution, then there is no way that there are survivors, because on the whole line, if you had one survivor, then by ergodicity, you would have not one, but infinitely many survivors. And unless they all have the same velocity, this would eventually end up in collisions. So if you take a continuous distribution of velocities, like uniform on -1, 1, then you don't have any survivor, but you can still wonder about the decay of density of particle. And that was interesting in particular if you think of this as a model for chemical reactions. Still, if now you have mu, you have distribution, this velocity distribution that has atoms, so some velocities have a positive probability of happening, then there might, in principle, be surviving particles. And this is the kind of phenomenon that we'll try to understand. First, by looking at special cases. So the general case is still very much open, but you can get interesting models by making it more combinatorial looking, by taking discrete velocities. So the first case would be the case when you have only two velocities, +1 or -1. So in this case, the combinatorics gets much simpler. In this case, in fact, the spacings don't even matter. Here on the picture here, I took unit spacings, but the collisions do not depend on the spacings. And as you know, what you get here is a kind of pairing of parentheses, and you can relate this to simple random walk, to discrete trees, and all kind of combinatorial structure. You can compute a lot of quantities here. In particular, you can get that the density of particle at time t is related to the return time of simple random walk, just because it means that you have a collision that lasts time 2t. The probability that some particle lives beyond time t means that its pair is beyond location 2t, and that corresponds to a return of simple random walk happening at time later than 2t. So you know in particular that this density decays like root t, well like 1/√t. And so many quantities can be computed in this case, and it's even possible to describe at large time what happens to the flock of particles. So if you take a large time, you have fewer and fewer particles, and they tend naturally to align. Like you would have lots of particles going to the right, then a big space, then many particles going to the left, for instance, a big space, and so on. And you can you can actually describe a limiting distribution for this distribution of particles. It was done by Ballistic and Ferrari in the 90s. But in this case, if you have only +1 and -1, and here I'm considering symmetric, I didn't specify that it's assumed to be symmetric, you cannot have survivors. The first situation where you can have survival is if you have considered 3 velocities. So now this is what it looks like. So this has been first defined by Ben Naim, Redner, and Levraz in 1993, and by Piaseczewski in 1995. So again, now if you start by a Poisson point process and have particle move either at 0 speed, so they will be called static particles, or speed +1 or -1. And again, we assume distribution to be symmetric, so +1 and -1 have the same probability. Then you get this kind of diagram here. We can have two kinds of collisions, either +1, -1, or +1 and 0, or -1 and 0. And in principle, you can also have surviving static particles that are never hit. And already in this case, it becomes, the combinatorics become quite intricate. There is no simple algebraic way to check survival. Not like in the case of two velocities, when you just have to add the +1s or -1 and check which time when it goes back to 0, for instance. Here there is no such simple rule, in particular because it depends on interdistances. If you have one static particle and two moving particles going towards this static particle, of course, it depends on the distance to find out which one will hit first this static particle. So and also, like in the +1, -1 case, you have long-range dependencies because of this heavy tails of the return times of simple random walk. And very crucially, you don't have monotonicity in this model, in the sense, for instance, that you're just adding more static particles doesn't necessarily help static particles to survive. I mean, in a finite configuration, for instance. Or if you switch some 0 velocity to a +1 or +1 to a 0 or something, there is no, this has a long chain of effects, and it can go either way. There is really no simple, at least that we could understand, that we could observe, no simple monotonicity in this way. There is no coupling that naturally appears. So let's look at simulations. So this model is the model that we will be discussing in this talk. So the symmetric 3-speed ballistic annihilation. So let's look at simulations. So there is one parameter here. It's the density of static particles. It's called P. So there are density P of static particles and 1 minus P/2 of +1, and the same for -1 particles. So first picture here is for P equals 0.24, which is just below 1/4. Of course, this is a finite configuration. And in this picture, in red, I hope you can see that you have the surviving bullets, surviving particles. And you can see that there is only one static particle surviving, and a bunch of moving particles surviving on its side. At 0.25, just below, you have more of an equilibrium. I mean, in the middle, you have a series of static particles surviving. And as soon as you get to 0.26, then the situation becomes strikingly different. You have an overwhelming proportion of surviving static particles. So these three configurations here are on the same scale on the horizontal axis. The vertical axis is just stopped as soon as every collision has happened. So as you can see, it happens very fast in the last case. So every collision happens very fast, and then you have every remaining static particle that is surviving. So based on these simulations, we conjectured, of course, that you have a phase transition at 1/4. And then we discovered that this had been also conjectured in the 90s by physicists, and even computed somehow by Piasecki and others, who also gave asymptotics for densities. So they have a very involved paper. I mean, technically involved. They are able to find a partial differential equation satisfied by some probability density function related to the model. So it's already quite a long partial differential equation, and then after pages and pages of computation, some of which include formal steps, they're able to obtain this critical value 1/4 and to find asymptotics for the densities. But as I said, there are some steps that are not quite rigorous or based on physical arguments. And also, it was very complicated. And our main result that we'll be discussing here is that indeed there is a phase transition at 1/4, and even we're able to find a rather simple proof for this. So it's rigorous and much simpler. Moreover, just like in the physics paper, we get the probability that the particle at 0 survives infinitely, which is given simply by 2√p-1 squared. So it's 0 below 1/4, and it's equal to this positive quantity after 1/4. In particular, we can even make a diagram showing that for values of p, the relative proportions of different types of collisions. So either +1 with -1 in green, +1 and 0, or -1 with 0 in red, or surviving zeros in blue, which appears only after 1/4. Something that is also interesting in our result here is that actually it holds for any interdistance distribution as soon as you have as you don't have atoms. So the absence of atoms here is only to prevent appearance of triple collisions. Otherwise, you can have the same interval on the left and on the right of a static particle, and therefore have 3 particles, 0, +1, and -1, colliding at the same place and the same time. So to prevent this from happening, we assume interdistance distribution is atomless. Otherwise, you just get i.i.d copies of this interdistance, and the result is the same. Well, so it's not dependent of the interdistance distribution. I will come back to this later. And furthermore, we also have asymptotics for the densities of particles. So C0 is the density of stationary particles, of static particles at time t. C plus is the density of moving particle, well, let's say +1 particles. And well, if you consider densities with respect to the distance, then you have to normalize the distance somehow. So we ask that the interdistances have a unit expectation, and also for technical reason we ask that they are exponentially integrable. Then we get this asymptotic. So for in the subcritical regime where every particle gets annihilated, density of static particles decays like 1/t, while moving particle decays like 1/√t. So the static particles vanish before the moving particles. At 1/4, both decay like t to the -2/3. And after 1/4, so you get a limiting density of static particles. And the convergence here is exponentially fast in time, so which is rather in accordance with the simulations where we had a very short time before we reached the final configuration. And similarly, of course, in the moving particles have an exponentially decaying density as well. So here in this result, I'm also giving the constants in the asymptotics, except for the first order in the exponential decay. And again, the reason is that the constants here are universal in the choice of the distribution of interdistances. However, the exponential order would depend on the distribution. So for a given distribution, like in the paper for the physicists, they were looking especially at the exponential case, and they were able to compute, if not to justify, but at least to compute the exponential order. in this case. So we also have tools that could be used in particular cases to get the exponential order, but it depends on the interdistance distribution. All right. So I'd like in the second part of this talk to give a sketch of the proof of this result, and discuss in particular the questions about universality, the fact that it doesn't depend on the interdistance, on the distribution of interdistances. So first, actually, I will focus on the simplest result, the critical value 1/4, and this asymptotic density, I mean the probability of survival, that is 2 root p minus 1 squared, with the positive part. That means it's 0 if p is smaller than 1/4. Let's start by a few remarks. So first, like I can make a small drawing here. So I'm interested in theta of p, which I repeat is the probability that the particle at 0 survives. So in particular, this implies that this particle has to be a static particle. Since by symmetry, if +1 particles could survive, then by ergodicity, you would have infinitely many such particles surviving. But by symmetry, you would also have -1 particle surviving, and this is not compatible. So the only particles that can possibly survive are those with a 0 velocity. So this, how can you compute this probability that this particle at 0 survives? Well, for the particle at 0 to survive, it means that it's neither hit from the right nor from the left. So you cannot have particles hitting 0. And these two parts of the environment are independent, because they are separated by this particle at 0. This is stationary, and by independence, these two events are also have the same. I mean, by symmetry, these two events have the same probability. So in the end, theta of p can be obtained, but as p, so probability at 0 is static, times the probability that there is no particle hitting 0 from the right to the square. If you look only at the right part of the axis, you're asking that there is no particle hitting 0 from the right. So here, by this picture, I mean that sorry. Sorry, I cannot erase for some reason. Yeah. Correct. So if you look at, so theta of p will be equal to p times the probability that no particles on the right-hand side. So starting with the first particle that would be at x1 and x2 and so on, no particle reaches the vertical line at 0, reaching the position 0. And in fact, it will be easier for us to define the complement probability q. That would be the probability. So again, if you look at only at the right axis, that some particle will hit 0. So this will be our main quantity of interest. So this would be p times 1 minus q squared. Okay, just by independence and by symmetry. So this is what is written here. And one interesting remark here is that since we have only +1 or -1 velocities, or 0, this if some particle, if it's the case particle here that admits 0, with location xk, checking that this particle hits 0 only depends on what happens between 0 and xk. There is no way that this particle can be caught by a faster particle on the right. So that will be very helpful in following. So remember that Q is this probability that 0 is hit. So 1 minus Q is the probability that, again, on the half axis, there is no particle reaching location 0. So what we will do is split this probability depending on the value of the first velocity. I mean, velocity of the particle at x1. So either it is static. So if it survives, then indeed 0 is never hit. So it means surviving for x1 means that it is static, probability p, and no particle hits x1 from the right, so probability 1 minus q by invariance by translation. Or x1 is static, but it's hit from the right, but no particle overflies this triangle, meaning that the location on the right here is not hit from the right. So by independence, you get that it's p times q, probability that the bullet at 1 is hit from the right, but this location is not hit from the right, 1 minus q. Or you get this kind of triangle. You have a velocity plus 1, it's hit by a minus 1, but no particle overflies. So you get some quantity alpha. It's the probability that you have this triangle here, times 1 minus q, probability that no one hits the dashed line here. Or you have a plus 1 that hits a 0, and no one overflies on the right. Well, no one even hits this vertical line here. And so how do you compute this last probability? Well, it turns out that you can simply flip the whole configuration between x1 and this location here. Distribution is symmetric, so if you mirror everything, you get the same distribution. And you get back to the second case that we had there. So this turns out to be the same. It's also pq times 1 minus q using symmetric. So you get a first equation here, which you can simplify by 1 minus q to get a relation between p, q, and alpha. But you need the second equation. So let's work the same for q. So probability that 0 is hit from the right. Again, we decompose according to the velocity of the first particle. If it's minus 1, then okay, we are done. 0 is hit from the right. It can also be static and hit from the right, but some other particle flies over. So here again, you decompose. It's pq square. You have two particles that are hit from two locations that are hit from the right independently. Or you have again this plus 1 minus 1, and it's flown over by some other particle, alpha q. Or alpha of this is a plus 1. It's hit from the right by well, it hits a stationary particle, and something flies over. This one is a bit more subtle because the particle coming from the right has to fly over this triangle here. If it's too close, then it will hit this particle, the static particle, before the one at x1. So we won't get this situation. So here you don't have independence between what's on the left and what's on the right. Still, if you mirror this situation, what you get is that particle at x1 flies over the triangle that you get from particle in the middle and the one at that location here that would collide. And if you can take both events together, this and the flipped event, then all you get is that there is a static particle somewhere that is reached both from the left and from the right. And because of symmetry, you have actually the same probability that it's the particle from x1 or from the right that hits first. Well, actually, to make this formal, you have to condition on the location of this particle here. But still, you can make this argument work and justify that in the end, it is just 1/2, because there is the same probability that it's the particle at x1 that reaches first or the one from the right, times pq squared. So p probability that it's static here, and q squared it hits both from the left and from the right. So now you have two equations which are not the same. If q is not equal to 1, then you can use the first equation, divide by 1 minus q, and get alpha in terms of p and q. Inject in the second one, you have alpha here as well, and get that q is 1 over root p minus 1. So this is the main combinatorial part in the argument, so which in the end is rather simple when you think about it. But you are not quite done, because since what you get is that either q equals 1 or q equals 1 over root p minus 1. So which one is it? So one would be the red line here. 1 over root p minus 1 is the blue curve here. So first, of course, if p is small enough, then this value 1 over root p minus 1 is higher than 1. So it cannot be a probability. So since q is a probability, it has to be 1. So this already proves that for small p, for p up to 1/4, necessarily q is equal to 1. So in other words, 0 is hit almost surely. So there is almost sure annihilation of static particles. What also is clear is that at p equals 1, you can get convinced that q is equal to 0. A static particle cannot be hit from the right just because there is no moving moving particle. So what happens in between? So you could use a physical argument to justify that it has to be this slope here. But if you want to make that regress, then it's not that easy, because what you would typically like to say is that that q is decreasing and that it's continuous. But as I said, in the present model, we don't have monotonicity that can be proved by comparing configurations for different values of p. You don't have a coupling that will work in a nice way. And it's not even clear that also that you have continuity. But still, so you still need some regularity of q. So q again is probability that on the half line 0 is hit from the right. So one direction is simpler. You can prove that q is lower semi-continuous. It's an increasing limit of continuous functions, simply because to check that 0 is hit from the right, you can check up to distance k. If 0 is hit from the right by distance k, that it's also true for larger distances, since, as I said, you cannot, if a particle hits 0, then it cannot be hit from the right itself. And this depends on a finite configuration, so it's a polynomial in P. It's indeed continuous. Using this, you can get that the set of supercritical probabilities, the set of subcritical probabilities, so P larger than 1/4, where Q equals 1. This set is equivalent to having Q strictly larger than 1 over root P minus 1, because we know that we have only these two roots. And now if Q is lower semi-continuous, then this set here is open. So using both the fact that you have only two roots and that you can approximate Q by continuous functions, you get that the set here is open. So now, in order to use connectedness of the interval 1/4 1, you need to prove that it's also closed. For instance, if you want to get that it's equal to the empty set. And this part is a bit more tricky, but you can also have a similar scheme to approximate the supercritical phase by finite condition. I mean, having a condition that depends only on a finite number of sites, that would imply that 0 is not hit. We can actually find a sequence of simpler models such that if 0 is not hit in the simpler model, and it's neither hit in the actual model. And for the simpler models, you can have explicit conditions that are continuous. So in the end, to say that Q is less than 1, it's enough to say that there is some model for which some quantity phi p is positive, and then you get that this set is also open. So I will not discuss this in detail. Like I can talk a bit more about this in the end. So in all in all, you can indeed just justify that that's the set of p strictly larger than 1/4, where q is equal to 1, is both open and closed. So since the set 1/4 1 is connected, then the set of values where q is equals 1 is either empty or the whole set. And but you know that at 1 you have that q equals 0, so it means that it's actually empty. So so you indeed get that the phase diagram is as follows. There is 1 up till 1/4, and then it has to decay like this to the value 0. So in the end, we have to spend as much time discussing, explaining why q is either 1 or 1 over 1 root p minus 1, as we spend time justifying that it's finding out which one it is. And just because we don't know much a priori about the model, we cannot easily compare from one value of q or of p to another. All right, and now I'd like to discuss universality. The fact that in this proof, if you look back at what we did here, we do not use anything about the distribution of interdistances, except that you don't have triple collisions. But as soon as you don't have atoms in the distribution of interdistances, then the proof works the same. So in particular, this value 1/4 is the same for any continuous distribution. And also the value 1 over root p minus 1 is the same. But this is not just because it's the same model. The model genuinely depends on the distribution of the distribution of interdistances. For instance, if you look at this configuration here with just 5 particles, so this is +1, 0, +1, -1, -1. In order to get this kind of situation where the first particle overflies and then survives, that means that the first distance has to be at least equal to the sum of the 3 other distances. And this cannot happen if for instance, the distances are all supposed to be very close to 1, or like here, uniform in 1, 2. So having a different distribution can make it really makes a different law for the pairings of particles. But still, the symmetries that we used are still valid in any case, and it's only the symmetries that make the phase transition happen at 1/4. So this is quite interesting that we have actually not one but a series of models that are all really different but have the same kind of phase transition. And we actually have even stronger universality. Like in particular, if you look at the index of the first particle on the right of the 0. So again, if you look only on the half line, look at the index, so the integer index of the first particle that hits 0 from the right, and call it infinity if no particle hits 0 from the right. So in the supercritical regime, if that happens, then this distribution does not depend either on the law of interdistances. So of course the distance to this particle will depend, but the index of this particle does not depend on m. And actually the first proof we had about that is just by showing that, like before, you can compute a generating series for this distribution. You get that it's actually rather explicit. You get well, or implicit, but it's given by a formula. It satisfies a fourth degree equation here, and this equation does not depend on m. So in the end, you get that this distribution does not depend on m. just because the proof works the same in every case. But what we don't have at this point a direct proof why it's the same. Note here that if you take x equals 1 in this equation, that you recover the equation that we had for q, which gave that q is either equal to 1 or to 1 over root p minus 1. And one another interesting feature about having this description of A is that you can derive the density of particles at the time t, as t goes to infinity. The idea for this is to find synthetics for p of A equals m. And indeed, if you have this kind of equation about a generating function, then it says that this generating function is can be analytically extended to some part of the complex plane. And to get asymptotics for the coefficients of the power series, you might know that it was enough to find asymptotics for this function close to singularity. So at this point, we have to do some complex analysis. So let me just state this very classical result you can find in Flageolet and Sedgwick's classic book on analytic combinatorics. That if you have a holomorphic function on the unique disk, and even in this Pac-Man shaped region here, with a singularity at 1, then if you have some asymptotic equivalent close to the singularity that looks like this here, then you can get asymptotic equivalent for the coefficients of f of this kind. So this is a very powerful result that you can apply in this case. So the only thing is that you need to find the singularities of this function that we had before here. So using this equation, then again using this equation, you can find the asymptotics close to this singularity, and therefore infer asymptotics for the coefficients. Okay. But still, we have an issue at this point, which is very similar, reminiscent of the issue that we had for Q. Actually, we have one equation, but two roots, 1 and 1 over root p minus 1. And here the same happens, that in fact, we don't have f of z, but we have an equation that has f of z, f of x as a solution, but it's a fourth degree equation. So après, you have 4 different roots for each given x. So what this defines is a kind of multi-valued analytic function. And in this case, you can find easily singularities of this whole multi-valued analytic function. It's not that easy to find which ones are singularities of f. So you have to dig a little bit more. And I can resist to show you a plot of this of what this might look like. So I can even have it move around like this. So this is the plot of the real part of the solution. So in the horizontal plane here is the complex plane. So the values for x, say, and in the vertical direction are the real parts of the 4 solutions of the equation that I had before. So one of these solutions is the generating series of A that I had here. So this is on my graph here, I have the 4 solutions for each given x in the complex plane of this equation here. So above each point in the complex plane, you have 4 different solutions. Actually, the one which corresponds to x is equal to 0 at 0. It's the sheet that you can see below here and above here. And so the question is which are the singularities of this sheet in particular? And in this plot, you can see it, for instance, that this point that I'm pointing with the arrow is a singularity of the multi-valued complex function. But it's not a singularity of f, because f is the sheet below. Its singularity is actually further away. It corresponds to the black line, while this one corresponded to the blue line. So we have to work here a little bit to find which are the singularities of F in order to be able to use singularity analysis. So the short answer is as follows. You can, depending actually of whether P is larger or smaller than one quarter. So this is how the phase transition happens. The singularities are not the same for F. They're the same for the whole function, but the singularities of the sheet corresponding to F are different. And this can be proved using the probabilistic argument that I had before, or in principle, it could also be obtained by purely algebraic arguments by studying the previous 4-valued function. From this, you get asymptotics for the probability that A equals to n, and therefore for the densities, because A equals n means that 0 is hit by the nth particle, so it means that it has survived until the nth particle, which more or less means that it survived up to time n if the interdistances are of order 1. So you can relate then the asymptotics that of the law of A to asymptotics for the density. All right. So this is what I wanted to present. So let me just give some concluding remarks, in particular about the universality. So I stated that this distribution A is universal, that this critical parameter PC, 1/4, is universal. And the asymptotics also have their first order that is universal, except in the exponential regime. But for instance, you can also actually prove that the whole skyline process is universal. So what is the skyline? If you look at the supercritical case, so you have some surviving ballistic, some surviving static particles, and in between, the other particles annihilate. And what you call the skyline is what you see from the sky in this diagram here. It will be the red shapes that I have here. So this sequence of shapes is i.i.d, and this distribution is also universal. So what happens below depends on M, the precise configuration of a distribution of triangles, which are either, let's say, pyramids or sharks. That depends on M, distribution of interdistances. But what you see from above does not depend, and also the number of particles in each shape. So it's a sequence of shapes and size of the shapes. So this is universal. It's actually even universal for a finite configuration. So in this case, you can also have surviving plus or minus 1 at the extremities. And even if you have fixed spacings, so spacing that are not random but fixed, except that they are shuffled. So in this case, you still get that the law of the skyline does not depend on the choice of the fixed spacings. So this is a more recent paper that we have. And finally, I would like to come back to the notion of triple collision that I eluded at first by saying that I will take continuous spacing distribution. So I cannot have atoms, but what if I may have atoms? Then triple collision might happen between +1, 0, and -1 particle. So what do you do in this case? One answer would be by saying that they all annihilate. So the 3 bullets disappear at the same time. In this case, you can still go through the same arguments. I mean, the one that I explained in details using symmetry about Q, except that there is some quantity that you cannot compute. Obviously, there is a triple collision at 0, but still you can approximate this quantity and get bounds. So for instance, you get that if you take unit interdistances, then you get extension for P smaller than 0.23, and survival for P larger than 0.24. So in particular, the critical probability is not 1/4 anymore, but you can approximate. And again, since you don't have monotonicity, you cannot even prove that that there is only one point when the phase changes. A priori, it could happen that the phase changes back and forth between these two values, even though we don't believe it's the case. Also, alternatively, you could also say that after a triple collision, collision, well, you can view this as an approximate continuous collision, saying that actually there is one of the moving particle that would hit the static particle before the other one, but just before. And in this case, you say that you choose uniformly at random which one of the +1 or the -1 survives. So that's actually a good way of doing things because it preserves universality. In fact, you can adapt all the arguments that I said before to this case. So there is no reason in the end to assume that you have no atoms. You can put atoms and resolve triple collisions in this way, and everything works the same. And this is also interesting in a theoretical way because this enables us to get a direct proof of universality. We can actually, so the proof that we had so far that I obtained from the argument that I gave is that for no matter what the distribution of spacing is, you get the same behavior in the end. But just because the same proof works, in this case, but we're also able to find a proof that really takes two different distributions and match them together. Well, it's actually you can continuously deform one distribution to the other. If you make a local change, that it doesn't change anything, but along the path from one distribution to the other, you have to go through situations where you will have triple collisions, and because you can handle these triple collisions as well by this choice here, choosing that you resolve uniformly at random, then you can indeed show that the distribution does not, that the behavior, for example, the law of the skyline doesn't change when you switch from one distribution to the other. So you can find a path along which the distribution stays the same when you deform one distribution to the other. So this is one way to have a better understanding of the universality. And finally, let me emphasize that even though what we did here is rather specific to this model, it's interesting to see that the methods have been adapted to variants of the model. So last month, there was a paper by Benitez, Younger, Liu, and other co-authors that extended the arguments to the case, so still symmetric, but in the case when you allow, after a collision, one of the two bullets to survive with some probabilities. So you get extra parameters. You get in the end 4 parameters corresponding to a probability that after a +1 -1 collision, it is a +1 or -1 survives, or a 0 that emerges, or everyone disappears. And similarly, for 0 +1, you can have a parameter to choose if it's the 0 that survives, or the +1, or if no one survives. So anyway, since everything stays symmetry, you can work similar arguments. Well, you have to extend a little bit the techniques, but it works the same. And you can find a critical value which is not anymore 1/4. But except that since you have more parameters, things get a bit more involved technically, and in the end, you cannot. The authors are not able to deal with every case, but in principle, the method works in any case. At least they are able to solve many situations. And finally, if you break symmetry, if you have like this velocities +v and -1, or if you have +1 -1 but with different probabilities, then you can still carry on some of the analysis. So this has been done by Younger and Liu. So in this case, you don't get the exact critical probability just because you have too many unknowns that appear. But still, you can get that there is a phase transition, and you can get bounds on this probability where this happens. Well, but again, you get extension below some threshold, survival above some threshold. But because you don't have monotonicity, you cannot prove that there is one critical value. Okay, and so this is the end of my talk. And just to come back to the initial problem about bullets. Well, what does this tell us about bullets? Not much, I guess, except that there are probably a lot of interesting problems that can be derived from this initial problem that we had. So I just can come back to this first slide. So this one, this was the bullet problem. So the first question is still open, but at least it shows that there are many cases where when you can do nice combinatorics and have interesting answers. So, well, this is, I guess, an invitation to keep working on this problem and looking, for instance, at other special cases, which, oops, sorry. I don't know what happened. Okay.
Okay, maybe.
Well, thank you.
Yeah, no, thanks for the nice talk, Laurent. Yeah. So we're a few minutes over, but obviously, if people want to ask questions and hang around, we can do that. So if you have a question, just please, feel free to ask it directly.
Yes, I have a question. It concerns whether you could have the particles sitting in 2 dimensions rather than 1 when they start, but moving in different directions, but annihilating if they come close enough to one another. Is there some sort of multidimensional version that you could think of?
There was a multidimensional version. It was known as meteor annihilation. Apparently it was introduced by Benjamini.
Mm-hmm.
But essentially nothing is known about it, but indeed it's been considered.
Right.
A quick question: are there any peaceful applications of this model?
Well, some people prefer to speak about balloons instead of bullets, but otherwise, which feels more peaceful. But I don't know. Well, you can just think about chemistry. Well, for physicists, the idea is to have a new model of chemical reactions. Usually, the models are based on diffusions, but you can wonder what happens for ballistic movement of particles. So this was the initial motivations, and they actually have a lot of interesting simulations. So there are many papers in the physics literature that work about on the continuous case, and which are motivated by understanding what happens for chemical reactions.
Thank you.